Okay, we pulled out one model, that is model 1 from the EYA-NMR structure, okay, and that is model 1.pdb. Okay, and there was a problem or a mismatch with the naming scheme that was in the model 1 as compared to the naming scheme used in the AMBER 99 SDILD enforcement. So you have to match those names together. Okay, that's why we changed the names. Okay, I ran a script on model 1, okay, and that changed the names. You with me? Right? And so once you change the names, we use one of the tools of Romax called PDB2GMX, and that PDB2GMX applied this as the input structure, okay, and it did two things. It used this so-called the top file, which has the topology, the common bonds. It identified all the bonds, angles, dihedrals, charges, momentum, and it also created another file, model 1 union PDB2GMX. Okay, and the difference between this and this file, the difference between the names of the atoms and the order. Okay, it did not change any of the coordinates. So, is everyone there? No, why not? So, should we go through this again?
Yeah, can you please tell me how to rename this?
All right. So, we're going to remove model 1, rename this. I'm going to remove model 1, rename this. I'm also going to remove the topology file. Okay. All right. Up to here is fine. Okay. So this is the little script, okay, that renames the atoms. Okay. All it's doing is it's using this Unix shell command called sed. Okay. And sed can be used for various different things. One of the applications of sed is it allows you to access specific text and change that text in the file. Okay, so what it's doing here is, if you look at, for example, any of the lines, sed minus I and minus V are options for sed. So you can find out what these options are. If you ever want to find out what a Unix command does, in Unix just say man that command. Okay, so if I say man sed, it tells me what sed does. Okay, and to get out of that, just press Q and you can put out of it. Okay? It's a stream editor for filter transforming text. It's very good for text editing. Okay, and when you get out of that, Q. Okay, so what sed is doing is it's looking for, this stands for look for all of them. Okay, so it looks for a string. So S looks for what string? It looks for this string HP3 tyrosine. That string should be in the file, so it can include spaces in the middle. We take this string and replaces that string with this one, and G means for all of them, all instances you find. You go and change it, but where does it find that input? That is in this $input PDB file, and that is defined up. That $input PDB is defined up. That is model 1 rename h.pdb. Okay, so if you want to rename certain atoms, all you have to do is you can use this file as a template. Okay, change the name of the input file up there using vi. Okay, and whatever atom names you want to change, just change them in here. Yes.
I'm sorry, what did you type in to get all this output?
Huh?
What did you type in to get all this output?
This is just a file. This is this file. Rename atoms amber.sh. It's a shell script. Okay, so the way Unix is made is Unix is mostly written in C. Okay, and when you type in something like ls or cd, what you're really doing is you're executing a C code that is written in C. Okay, that's when you do cd and ls. The same way when you write sed, you're actually running a C code. Okay, and if you put everything inside a single file, okay, you can put all the commands you want inside a single file. Okay, and put this on top, which means it's now a shell script. Okay, that's all you need to put on top. and then define all the variables. Okay, the only variable here is this model 1 rename PDB, and this variable, this is a variable name, and that's its current value. Okay?
How do you get the shell file?
How do you get it? Oh, okay, use that one too. Right. All right, so you can copy this from, so all the files that we're going to share as part of this class are stored under, so if you do a cd/, it takes you to the root directory of the cluster, okay? And within the root directory, you're going to see shares. cd to shares, and within shares, you're going to see all these different courses. Okay, this is our course BSc 6932 with my initials. Okay, we change to this. Okay, and I've created two directories here. One is the source directory and one is Camden related stuff. Okay, so in the source directory you have this code. Okay, you take this code and you copy this into your working directory, wherever it is. Okay, so if you start with ~/ that takes you to your home directory, and working directory is Camden. She's going to put it there. You change back to your home directory and go to Camden, and that's what it is. Okay? And if you look at, then you can open this shell script. Okay? You can go on top. Right now, the input value or the value of this variable into PDB file is model1 edited. Okay, but that's not the file name that we have. Okay? Our file name is rename H, right? You change it, escape, colon, WQ, okay? Okay? So what I'm going to do is, I'm going to now copy this file, model1.pdb, and I'm going to call it the file that I named up here. Okay. So model1.pdb and model1 rename h.pdb are exactly the same thing. Okay. Is that good?
Scrolling up like a smidgen where you change the name
So this is
at the top. Yeah.
You can call it whatever you want, and then when you copy model1, you copy exactly the one. You all caught up? Okay, then in order to run the script, all you have to do is say sh / rename and number. Now if you look at the model1 rename h, increasing the font size. If you remember, one of the items that was not, so this is the one that we had to change, right? HB3 had to be changed to HB1. So it tells you that it's actually working.
Thank you.
Okay?
You're Sure, anything.
Okay. We good?
Don't worry, I'll figure it out someday.
No.
I'm still trying to figure out how you just open the file in the program, so
Okay.
don't worry.
Don't worry.
Don't worry.
Don't worry.
I'm not worried.
All right. It's a small class, so I look at everyone. Right?
Yeah, I think it does.
Don't worry.
Okay.
Second.
So we're going to take this file, model1 rename.hpdb. Now this file is ready
Just
to
the rename.
to feed it into PDB to GMX. Okay. And before we do all that, we have to load the module. Right? Remember, it's not going to be loaded automatically. So the module avail. I can never remember the name of the module below. We'll look for it again.
Might be this one. Space first.
Module code. Then I'm going to run PDB to GMX. Okay. So PDB to GMX requires lots of different inputs. First, you have to supply the name of the PDB file, which is okay. Name of the output file. Call this.
That output, you can change the name there to whatever you want.
Yeah, it's an output, so it's a name of the file that you want the output to be stored, so it's user defined. Okay. Okay. Minus F minus O. Okay, and then you're going to go minus inter. Remember, minus inter was the interactive assignment of charges and disulfide bonds. Okay. You can also name whatever topology file needs to be named as. You can call this minus P, whatever name you want. If you don't name it, it's going to be named as topol.top. Okay? Now you're going to select 6 from here. Okay? For the force field, the water type is going to be SPCP, that's going to be 5. Okay? And then it's going to start asking you questions on what charges to put on the arginine. Arginines are normally positively charged. Okay? You're going to choose 1. This arginine is also +1. Aspartic acid is negative 1, so it's going to be 0. Glutamic acid is going to be 0. And now it's asking whether the cysteines are type. You need to connect these 2 cysteines to the disulfide bridge. Okay? Right? So you can say yes to that, yes to this, and yes to the third as well. It's done. Yes.
In general, if they give you like a quote from Matt or Shakespeare, that's like a good sign.
That doesn't matter.
Okay.
so Gromax has all these 100,000 different quotes in there. So every time you run it, it's going to give you something different. And when there will be a time when you will see that they're starting to repeat, it means you have used Gromax quite a bit now. Because as long as you keep seeing the same quotes, you still need to run Gromax anymore. Alright, so this created these files, so files at the top. Create another one called POS3.ITP. Okay? And this model 1 renamed HPDB. Okay, here the atoms are renamed. Now the order of naming of atoms here in this model 1, look at the way the atoms are ordered: N, H1, H2, H3, C is HA. Okay, this is the same order that is in the topology file. Okay, N H H H. Okay, N H 1 H 2 H 3 C A. So the ordering of atoms in the topology file has to match the ordering of atoms in the output file of PDB to GMX. Because beyond this point, when Bromax really runs, it forgets what atom it is. Once its attributes are defined, it is only recognized through its index. Is it atom 1, 2, 3, 4, 5? Okay? Right? Are we good? We good? All right. Now that we have a topology file, we have a PDB file. Okay. Now you want to take this file. This is our current PDB file. And you want to take this file and you want to put this inside a box. Okay, so that you can do apply periodic boundary conditions, maintain pressure and temperature. Okay, and the origin of the box is always going to be 0, 0, 0. Okay, and all the coordinates will be positive. It creates a positive box in the positive real space. So now, if you look at the coordinates of model 1, several of these coordinates are negative, so it's got some orientation. That orientation is in the crystal. Okay, so what you're going to do is you're going to take the center of mass of this protein and you're going to put it inside the middle of a box that you define. Okay, and to do that, you're going to use a command called edit conf. Edit conf. This is basically just short for edit conformation. But now you want to change the conformation. So edit. Edit conf does a lot of different things. So one of the things it does, it allows you to put the protein inside a box. Okay. Again, you have to provide an input file. The input file is model 1. That's your input file. Okay. Supply the name of an output file. Okay. Model 1. And I'm going to call this, I'm going to just add underscore box to it so I know that this has been put inside a box. Okay? Now, how big a box do you want? That's the question. You can supply the box dimensions right after minus box. So what should be the length, width, and the height of the box? Okay. Normally what you want to do is you want to leave 1.5 nanometers on all sides of the protein. Okay? So that the two proteins, the protein in the main box and the protein in the image, is separated by 3 nanometers. Okay? If it's closer than that, it is going to start feeding each other. Okay? Generally, at about 3 nanometers, the proteins don't, technically feed each other. Okay? Technically they do, but physically they don't. Okay? So, but how do we know what the size of the protein is? Okay? So normally when I don't know the size of the protein, I just create something random. Okay? I just provide a really large box, and this is in nanometers. Okay? I know the protein is very small. It is something of the order of 3 to 4 nanometers big. So I really give it a really big box. Okay? And say enter. Okay? And then the script runs. So when this code runs, in the end it tells you what the system size is also. Okay? So it says the system size, which is in this case the protein size, is 2.7 nanometers, 3.2, and 2.1 nanometers. Okay? That's the size of the protein. The rest you don't care about at this point. Okay? Because you ran this only to find out what the size of the protein is. Okay? So if the protein maximum size is 3.3 nanometers, if you choose a box which is 6 nanometers, it should be about 3 you should have left 1.5 nanometers on both sides. Is that okay? Roughly. Okay. Now, that is what we normally use. We leave 1.5 on both sides. Now, the problem is the bigger the box size you choose, the better it is for you, right? You have a much better physical system. But the bigger box size you use, the more water you have to put inside it, which means more atoms you have inside, which means it's going to take a long time to simulate. Okay? So you want to pick the smallest possible size you can. Does that make sense? Okay? And since this is more of an academic exercise, it is not really used for publishing. You want to get results much faster. Okay? So what I'm going to do, instead of using a 6 nanometer box, I'm going to use 5 nanometer box. It's going to reduce the number of waters quite significantly. Okay, but since this is just an academic exercise, we can do it with 5. Okay, but if you want to do this for publication, make sure you have 1.5 nanometers on both sides. Okay. I'm going to choose a box of 5, 5, 5. Okay. And this time I'm going to put something else in there just to make sure that I remember what the box size is. 5. It's a cubic, and the reason you might also think that since this dimension is much higher than this, I can put 6 nanometers here and 5 here and 5 here, and I'll be fine. But that's not really going to work. And the reason it's not going to work is because when you run a simulation, the protein tumbles inside. Okay, the box might be wide on one side, but the protein starts tumbling. Okay, and then the other side becomes much smaller than what's needed. That making sense? Okay, and you will see the protein tumbles and moves around a lot inside. Okay, so I'm going to choose a box of 555 and enter. Okay, and now the other lines make more sense. Okay, so what it did was it found the center of the protein. It was around here. It was pretty much close to the. It was pretty much close to 0, where the center of mass of the protein was. Okay, and it took that center of mass and it made it the center of the box, 2.5, 2.5, 2.5. Okay, so it translated the whole protein to the center of the box. Okay, is that good? All right. And then you can remove the previous one so that there is no confusion later. You don't need that anymore. Okay. So now there are 3 sets of files here, 4 different PDB files. Just to recap, we started with model 1, renamed all the atoms that was necessary to match their nomenclature in the force field. Okay. And then you ran PDB to GMX to create the topology file. Okay, and reorder the atoms in here so that the order matches that in the force field file as well, in the topology file. And then you put that inside the box. Okay. Now, if you're doing implicit solvent simulation, that is, if you're describing the water as an implicit solvent, then you don't need to add explicit water support. But at this point, you want to add, since we're going to go into the explicit water simulation, we're actually going to add the water molecules in the box. Okay. Now, the way the next code is going to work is we're going to use the next code to add waters inside this box. Okay. The way that code normally works is it tries to fit a water molecule in any empty space inside the box. If it can, it will put a water in there. If it can't put a water in there, it won't. And to speed up everything, what it does, it uses a template, a little tiny box. And it first puts that box over the entire big box, and then it removes all the waters which are outside the edges. And then for all the waters, it sees whether it's overlapping the protein. If it's not, it just keeps it there. If it does, if it overlaps, it removes it. Okay? So the code we're going to use for that is GenBox. Okay? So GenBox you can use for adding water. GenBox also requires inputs. It needs to know what the name of the input file is. So it's not -F in this case, it's -CP. Okay? Okay, -CS. -CS is the kind of solvent you want to add. Okay, and the kind of solvent we want to add from a little tiny box is called SPC 216. It basically has 216 SPC type waters. Okay,
Let's see.
SPC 216.
What does that mean again? That was tight.
So SPC, so we chose, when we were choosing the kind of water model we want, we
Mhm.
chose SPC/E. It's kind of an SPC water, but it has the /E, which stands for evolutionation. It's a special tuned water, but it's essentially a single point charge water molecule. So it has 3 point charges, each representing the oxygen and 2 hydrogens. Okay? You have more complex water molecules like Pt.4, Pt.5, which have 5 points, 4 points to describe a water molecule. Okay. So in this case, we're going to use SPC 216. Okay, 216 is the tiny little box that has 216 waters in it. Okay. And then you have this -O. What I'm going to do is, again, I'm going to append the previous file name with SPC. Now tell me that after the box, we added SPC in the volume. Okay? And this runs. So the bottom of this file is what is the most important stuff here. Okay. So like I said, what it did was it took the little tiny box of water and it used that box to fill up the entire big box. Okay? And what it did was reading solvent configuration. Okay, it read this SPC 216 box. Okay, this was the dimensions of the box in nanometers. Okay, there's 648 atoms and 216 residues, which is each residue has of water has 3. So this is 3 times that. Okay, and then once it did that, it filled up the box with small little boxes. It looked for. It's easier for me to see it here. Okay, it says generating will generate new solvent configuration of 3 times 3 times 3 boxes. Okay, and generated configuration, sorted that configuration, found one molecule type which was a protein, which was already inside that box, and then it says I'm going to calculate all the overlaps of that protein with these existing waters. Okay, and it removed these many waters from outside the box. Okay, and all this stuff here, and then in the end, there were 23926 water molecules in the box. Yes.
I got file input output error. What am I trying to do?
You got a what?
It says file input output error.
File input output error?
Yeah.
Is that?
Well, what does it mean?
And every time I replaced it, it will
Too long?
change like for things like documents or desktop and things like that.
Okay. These are the
So like I can say like,
Go back to the top.
so change documents.
Do you have a file like that in there?
Oh, maybe I'll check.
Desktop, it brings up the same thing when I realized I don't understand what it's there.
Oh, is it very binding?
Oh, you have a Grow. You don't have PDB. They're different formats.
Right?
Yeah.
That's cool.
Why would it do that?
Because the
what
previous
I had
command
issues
you
with
used
last
didn't
time, right?
specify
I didn't tell it
PDB.
to
So,
name
when I
PDB.
listed it,
Okay.
Okay,
so
so now this is going to work and you can.
he doesn't
Right,
look
no,
like
this
you.
it's on here.
Like, it doesn't look like
File input output
you know,
means it
desktop
just
files.
defines the